Hi guys, hope you're all well. I'm back again with another video on linguistics. So today we'll talk about syntax and parsing. So this is one of my favorite topics. I wrote a master's thesis on this 10 years ago. So I thought, I can give like a brief intro to this area to students of linguistics who are getting into NLP. And so I want to kind of show you the connections between theoretical syntax, which most linguists should have studied in their as part of their course requirements, and parsing. So the whole area of building automatic sentence analyzers in NLP. So these two areas are closely related, and so today we will talk a little bit about the connections between these two areas. And yeah, the first thing I want to say is this is a very high level overview. So I'll try to get into some detail, but then this is not an exhaustive sort of tutorial. And this is a huge topic, so we'll break it into many sessions. So today we'll just talk about grammar formalisms and the relationship with parsing. So yeah, let's start with some terminology. Let's get some definitions out of our way. So the first thing is syntax, right? So what do we mean when we say syntax? So in linguistics, what we mean by syntax is the structure of the sentence, right? So if you have a sentence like John saw the man with the telescope, then you have to analyze the structure of the sentence, and this sentence is ambiguous because there are two possible ways to analyze the structure. So you could attach the prepositional phrase with the telescope at the verbal level, so which gives you the meaning of like John using a telescope to see the man, or you could attach it at the noun phrase level to the man, and you would get the meaning that John saw the man who was carrying the telescope, right? So this is a clear example of how structure, predicts the meaning, and how ambiguity in structure can lead to ambiguity in meaning. And why do we need to analyze the structure? So if you're building any application which requires, which requires you to understand the meaning of sentences, which requires you to extract content, which requires you to extract like meaningful content from the natural language text, then you need parsers, right? And yeah, so this sort of work has work on parsing has, um, I would say that it has gone out of fashion in the last few years. There haven't been many papers on parsing. Also, although now it's changing, I've seen some recent papers on non-locality, neural parsing, etc. But this has been, so with the neural advances in like neural architectures, and everyone's moved to like neural network modeling of NLP problems. So they think, the general understanding is that this is not a relevant area, but that's not the case. If you want to build smart NLP systems, you need to have a full understanding of all the building blocks of NLP. So a parser is one of the most important modules when it comes to NLP, right? To building any sort of system which processes natural language. So yeah, so we discussed syntax. We know that syntax is the analysis of uh, the structure of sentences. And what is parsing? So parsing is exactly what we did just now. So we analyze the structure. So as humans, we do this all the time, right? So if you encounter a new sentence, you understand the new sentence by using the grammar that you have. So by grammar, I mean like the cognitive grammar that we have to parse the sentence and compute its meaning. So this is something that we do all the time. And in NLP, what we are trying to do is to build tools that can do this automatically. I'm sorry. So tools that can do this automatically. So yeah, so that's parsing, right? And so yeah, another point that I wanted to mention is this notion that neural parsers or neural neural network models don't use grammar. So this is a very important notion. So this is a misnomer, because as long as you are using an annotated corpus to train your model, there is a notion of a grammar in your model, because the human is using their cognitive grammar to annotate a corpus. So the annotated corpus contains an implicit grammar, and whether you use neural networks or whether you use any other machine learning framework, that machine learning algorithm is trying to approximate the human grammar, which went into the creation of the annotated corpus, right? So that's a very important notion that you need to understand. So even when you say that, okay, I'm using neural networks, it doesn't mean that you are, it doesn't mean that you're not using notions of like grammar, right? So yeah, let's talk about grammar, right? So in linguistics, when we use the term grammar, we mean a very specific. We have it's a technical term. It's not a term from everyday language. So in everyday language, when they say grammar, we are talking about prescriptive grammar. So there are rules that are taught in school about how to produce the right forms of speech, and how to produce and which forms of speech are incorrect, right? But then we are talking in linguistics, we talk about the cognitive grammar. We talk about the grammar that children acquire without any sort of teaching, right? So when a child starts speaking the language, and once they learn how to construct sentences, they develop a notion of grammar. They acquire the grammar of the language, and we're talking about that grammar, and that is the grammar that we use to parse sentences. So we don't really every time you have a new sentence, you don't think up all the rules that you have learned in school. So that's not how we parse sentences. So yeah, anyway, so let's go back into history a little bit. So yeah, so if you look at the definition of formal grammar, and if you look at the history of formal grammar, I mean, I really hate to do this, but this is something that is very I hate to be the guy who says that everything started with Panini, but if you look up even the Wikipedia page on formal grammar, the earliest known formal grammar is that of Panini, the Sanskrit grammar in Ashtadhyayi. So uh, Panini had a grammar to derive all the forms of Sanskrit, and also like analyze the sentence structure of sentences in Sanskrit. So that's the earliest known grammar in history. And if you look at the modern era, so Chomsky gets he gets the credit for being like the for being the first to introduce this notion of like production rules, etc., right? So I mean, introduce the concept of like uh, you know to develop the concept of formal grammars within linguistics. Although this is not true, there were a number of people working around that time, and this was a very rich area. So even if you look at the Chomsky hierarchy now, they kind of uh, acknowledged that there were other people working on this. So there was a French mathematician. I think his name is Paul Schutzenberger. So yeah, now it's called the Chomsky-Schutzenberger hierarchy. And then there were many more mathematicians. So there was Klein in America, and then there was I think there was Axel too he's a Norwegian mathematician, and this work goes all the way back to Leibniz, and there were so many people who worked on this topic. And yeah, Chomsky's own teacher at Penn, Zelig Harris, was a major proponent of this kind of work. So Zelig Harris had a number of students, and another famous student of Zelig Harris is Professor Arvind Joshi, the late Professor Arvind Joshi, who developed the formalism of tree adjoining grammars. That's a very interesting framework, and I had the good fortune to work with Professor Joshi. So we'll do another video about tree adjoining grammars, but in this video we'll focus on Chomsky's work. So in 1956, Chomsky wrote a paper called Three Models for the Description of Language, And Chomsky also worked on this topic for his PhD thesis. So he was working on, so if you look at his PhD thesis, which was later published as Syntactic Structures, you see a lot of discussion about how to use formal grammar theory to, you know, formal language theory to account for natural language syntax, right? So in 1956, in this paper that I mentioned, so it's a quite a dense paper, but then the basic idea is quite simple and straightforward. So I encourage you all to read that paper. I'll put the link in the description. So in that paper, Chomsky developed the notion of phrase structure grammar, and he also discusses different kinds of grammar. So he discusses, if you look at the Chomsky hierarchy, so Chomsky defines four different kinds of languages. So you have the unrestricted grammars, uh, which he calls the type 0 grammars. Then you have context sensitive grammars, which he calls the type 1 grammars. Then context free grammars, type 2 grammars, and regular grammars or regular languages, which are the type 3 languages. So the idea is that all these languages have increasing levels of complexity. So yeah, so the regular languages are the least complex, followed by the context free languages, followed by the context sensitive languages, and then the unrestricted languages. And if you look at the literature, so there is also work, all of this sort of is at the interface between computer science and linguistics. So in computer science, people also use these notions to develop the theory of automata, to develop the theory of computation. So when you have, so I won't get into these details too much because it will not be possible for me to, explain them properly, and I don't want people to be confused. So each of these different kinds of grammars is equivalent to a computational machine. So for example, regular grammar is equivalent to a finite state automata, and a context-free grammar is equivalent to a push-down automata, and context-sensitive grammar and an unrestricted grammar are both equivalent to Turing machine. So Turing machine is sort of a hypothetical machine, so we don't really fully understand how to implement that yet. But for context-free grammars and regular grammars, we understand how these are implemented, so we know the form of those grammars, etc. So yeah, and Chomsky goes on to point out that natural language is somewhere between type type 1 and type 2. So it's mildly context sensitive. It's somewhere between being context free and context sensitive. And so one of the consequences of this work is many linguists sort of assume that context free grammars are inadequate to describe the structure of language, and they went on to develop more complex formalisms, which can account for context sensitive phenomena in language. So yeah, we'll talk about these things, but first I want to kind of get some basics across. So I want to show you, like, if you're a student of linguistics, so all of this is already well known to you. So you probably don't know the terminology. You might not be familiar with the terminology, but if you have done a course on basic syntax and done any phrase structure grammar. So a phrase structure grammar is a kind of a context-free grammar, right? So I think I have, yeah. So I have like a slide here, if you can see, right? So this is a sample context-free grammar. So the basic definition of the context-free grammar is that it's a tuple, it's a four tuple, and you have four different elements here. You have n, which is set of non-terminals. You have sigma, which is a set of terminals, and these two sets are disjoint, so there is nothing common between n and sigma. And then you have p, which is a set of production rules, and then you have s, which is the start state, right? So we'll talk about all of these things, and as I said, this is just a high level overview. So I want you to go back and read about these notions. Um, but yeah, here I'll show you a toy grammar. So let's say we have these rules here, right? So S goes to NPVP, NP goes to det n, and n goes to either n can be either a cat or rat, and det, which is determiner, goes to the, and vp goes to v and p, and v goes to the verb ate, right? So the circled elements are the non-terminals. So a non-terminal is something which can be expanded further, and the ones which are underlined are the terminals. So here cat, rat, ate, the, these are the terminals. So they cannot be expanded anymore. That's why they are called terminals. And the production rules. So these are all the production rules that you saw here. So these are the production rules. And start symbol. So start symbol in this case is S, because the derivation will always start with the start symbol. So when you use these rules to parse the sentence, the cat ate the rat, you get a structure like this. So this should be familiar to linguists, right? So if you have taken a course on syntax, you know how to draw these trees. And you know how to draw these trees because you know how to write this grammar. You know how to write grammars like this, right? And then you have, so these are the definitions: terminals, non-terminals, and the start symbol. So this is context-free grammar. So next we'll look at regular grammar. Yeah, so regular grammar is the same as a context-free grammar. The definition is exactly the same, right? So again, G is a four tuple, non-terminals, terminals, sigma is the terminals, P production rules, S is the start symbol. The only difference here is in a in the production rules in a regular grammar, they are more restricted. The form of the production rule is more restricted. So here you can see that. So here is a sample regular grammar. The RHS. So yeah, so this is something we forgot to mention. So when you have a production rule, you have a LHS, which is the left hand side, and an RHS. So in regular grammars, the RHS can only have one non-terminal. Recall that in the case of context-free grammars, there was no such restriction. So one non-terminal can expand into two non-terminals, can be rewritten as two non-terminals. So there is no such restriction. But in the case of regular grammars, one non-terminal can be rewritten as only one non-terminal. So if you look at this sample grammar that I have here, so S goes to A is the non-terminal and AT, and then this A non-terminal can be any of these letters. So it can be B, can be C, can be E, it can be H. So what is the yield of this grammar? So what does this grammar generate? It basically generates the words bat, cat, eat, and hat, right? So you might also be familiar with regular expressions, right? So if you are a programmer, if you have written any like Python scripting, so you write regular expressions to capture patterns in text, right? So for example, so this is the regular expression to capture these four words. So you have the square brackets and then these four characters, so any of these can appear, and then you have the rest of the word, so AT. So this is the set of all words which start with one of these characters and have AT. So the set of three-lettered words. So when you write this regular expression, this is equivalent to writing this grammar. So regular expressions are basically based on this notion of regular language and regular grammar. Okay, so with these definitions, yeah, so now we know what's a regular grammar and what's a context-free grammar. So why did I tell you about these things? So yeah, as I mentioned, when these concepts were developed, right, Chomsky's take was that language is mildly context sensitive. So both regular grammars and context-free grammars are not adequate enough to describe natural language. So he went on to kind of develop other kinds of formalisms, which he thought were adequate for which were sort of like which had the right expressive power to capture all aspects of natural language syntax. But then in computer science, computer scientists took up this idea of like context-free grammars, and they developed it further. And there are they developed many efficient parsing algorithms using context-free grammars to parse not only natural language sentences, but you'll be surprised to know that most of the programming languages that you use today, most modern programming languages, are based on CFGs. uh, so yeah, regular expressions as well, I just talked about it. So you have, if you can write all these regular expressions to capture patterns in strings, etc. And then CFGs are used to parse any sort of statements in programming languages. So in the next session we'll look at one example where we'll take a Python statement, or any language, and then see how we can construct a CFG to analyze the structure of that statement. So yeah, anyway, so the point is that CFGs were developed further by computer scientists, right? Within NLP, there were many efforts to build parsers, highly efficient parsers to that can parse sentences based on CFGs. And so we'll do the next session on this, but you can read about. So there are multiple ways to parse. So there is top-down parsing, bottom-up parsing, and then there is chart parser, early parser, CYK parser, and shift reduce parser. So all of these different sorts of parsing techniques have been developed over the past 50 years or so. So it's a very rich area, and I'd encourage you to read about these parsing algorithms, even if you don't understand all of it. So you should, the basic idea that you should know is, if you're able to write a CFG, if you're able to write a context-free grammar, so there are different terms again. So this is another confusing thing. So there are many terms used for CFG. So they're also called Backus-Naur form grammars, BNF grammars, right? So the basic idea is that the production rules are context-free, as I showed you in this example. And so if you're able to write a grammar like that, then you can use any of these parsing algorithms to parse strings using that grammar. So we will talk about this in further detail in the coming sessions, but for now I just want you to understand this, right? And the other thing I wanted to mention was yeah, so there are so the argument that CFGs don't capture many aspects of linguistic structure, that is true, but then there are ways to sort of enhance the power of CFGs. There are various sort of tricks, and one of the things that I worked on. So if I actually shared my slides on LinkedIn, so people can take a look at it. So the slides are again quite dense, but they'll provide you a high level overview. So there are ways, people have developed ways to um, improve parsing, improve the ability of CFGs to capture linguistic structure with other like engineering tricks. So for example, instead of doing like deterministic parsing, you can generate n best candidates, and then you can use a re-ranker, which will look at which will look at richer linguistic features to pick the best parse. So that's exactly what I did for my master's thesis, and I improved the Stanford parser, which is a CFG based parser, by I think 4 percentage points, if I'm not mistaken. You can check the slides. But yeah, so there are various things here that are of relevance to linguists, and I think you can students transitioning from linguistics into tech can easily catch up by reading about these things and learning about the intersection between parsing and grammar formalisms. And so yeah, it's a pity that these topics are not taught in linguistics courses. So I mean, yeah, it's a shame that syntax today is completely lost its direction. And I mean, like, I mean, I know that I am saying things that will upset my former teachers, but that's my take on it. So yeah, so if you look at theories now, they just sort of create some jargon, and they find some exotic languages where they show that okay, the concepts that we proposed work. So there is no there is no interest in pursuing this kind of interdisciplinary research into like the interaction between parsing and syntax. But that's my area of interest, and yeah, so that will be a very useful exercise for any student of linguistics that's getting into parsing. And I think, yeah, I think this is already enough content for this video. And I think, yes, I'll put some readings in the description, and do follow up on those readings. And then next time we'll take a hands-on example, and we'll try to understand these concepts in further detail. Until then, have a nice time.